In this video, we'll be going over problem 10 in the January 2020 CXC Math exam. In part A, we're given a matrix transformation with the matrix M with entries 0, P, Q, 0. And we're told that it maps the point R to the point R prime, where R is the point 2, -5, and R prime is the point 5, 2. In the first part, we're asked to determine the values of P and Q. In general, if you have a matrix transformation, then for any input point x, y, the output is the matrix multiplication M times your point. So here, if I have the matrix 0, P, Q, 0, and I want to see where the point x, y gets sent to by the map, then I do the matrix multiplication, which gives us 0 times x plus P times y, and Q times x plus 0 times y. This simplifies to Py and Qx. So the input point xy gets sent to Py/Qx. In our problem, the point R gets sent to R prime. So let's write that in an equation. So we have that 0p/q0 times our point R, which is 2, -5, is sent to R prime, which is 5, 2. We can use this equation to figure out what P and Q are. On the left-hand side of this equation, if we compute the matrix multiplication, we get -5p and 2q. And this has to equal the right-hand side, which is 5, 2. Now, since I have two vectors that are equal to each other, their first components have to equal each other. So -5p is equal to 5. And I can use this equation to solve for p. Divide both sides by -5, I get that p is equal to -1. The second components of the vectors also have to equal each other. So I have 2q is equal to 2. Divide both sides by 2 to get q. I find that q is equal to 1. So that's the answer to the first part. P is equal to -1 and Q is equal to 1. Part 2 of this problem asks us to fully describe the transformation M. In part 1, we found that the matrix M is the matrix 0, -1, 1, 0. Now, if we apply this matrix transformation to an arbitrary point xy, well, the output would be the matrix 0, -1, 1, 0 times the point xy, which gives us -yx. So this transformation takes the point xy to the point -yx, meaning that it swaps the x and y coordinates, and then it negates the x coordinate. In part B, we have a parallelogram PQRS, and we have some vectors. The vector from P to Q we're going to label as U, and the vector from P to S we're going to label as V. We also have a point M on QS such that the ratio of QM to MS is 1 to 2. In part 1, we're asked to write certain vectors in terms of U and V. In A, we have the vector QS. In our diagram, QS is this vector right here. What we can do is think about QS as the sum of these two vectors. A vector from Q to R, and then a vector from R to S. So again, we want to think about QS as the vector QR plus the vector RS. The vector from Q to R, well, that's just the same as the vector V. The vector from R to S, that looks like the vector U, except it's going in the opposite direction. So we can think of that as -U. So the vector QS is QR, which is V, plus RS, which is -U. So QS is V minus U. In part B, we want to express the vector QM in terms of U and V. Since the segment QM is a portion of the line segment QS, we know that the vector QM is some scaling of the vector QS. So it's some scaling of V minus U. We are told that the ratio of Qm to Ms is 1 to 2. This tells us that Qm is 1/3 of Qs and Ms is the remaining 2/3 of Qs. So that keeps our ratio 1 to 2. So again, we have Qm equals 1/3 of the vector Qs. Since Qs is expressed as v minus u, we can write Qm as 1/3 of v minus u. In part 2, we want to show that the vector mr can be expressed as 1/3 times u plus 2v. Let's start by drawing mr in our diagram. This vector can be thought of as the sum of two vectors, a vector from m to s, and then a vector from s to r. So again, we can think of mr as the sum of ms and sr. First, let's express ms in terms of u's and v's. From our previous part, we saw that qm is 1/3 of qs, and we said that ms is 2/3 of qs. So we can express ms as 2/3 of v minus u. Then we have plus the vector sr. The vector sr is the same as the vector from p to q, which is the vector u. So that's what we add here. Now let's simplify this. If I distribute the 2/3, I have 2/3 v minus 2/3 u, and then plus u. This simplifies to 2/3 v plus 1/3 u. Next, let's factor a 1/3 from both of these terms. We get 1/3 times 2v plus u. Well, the 2v and the u can be reordered, so we can write this as 1/3 times u plus 2v. So we've shown here that the vector mr can be expressed as 1/3 times u plus 2v. In part 3, we're told that t is the midpoint of pq, and we want to prove that r, m, and t are collinear. So let's start by drawing t on our diagram. Let's draw in line segments tm and mr. In general, if we want to prove that 3 points are collinear, what we can do is look at the line segments tm, mr, and tr, and look at the slopes or the gradients of those line segments. If all of those line segments have the same slope or gradient, then we know that the 3 points are collinear. But instead of thinking about this in terms of slopes or gradients, we can think about them as vectors. This statement is equivalent to saying that the vector tm, the vector mr, and the vector tr all point in the same direction, meaning that they're all scalar multiples of each other. Let's start by writing the vector tm in terms of u's and v's. In our diagram, the vector tm can be thought of as the sum of the vector tq with the vector qm. So again, the vector tm is equal to the vector tq plus the vector qm. The vector tq is going to be 1/2 u, because we are told that t is the midpoint of pq. And qm we found previously to be 1/3 v minus u. So this is equal to 1/2 u plus 1/3 v minus 1/3 u. Simplifying this, we get 1/3 v plus 1/6 u. Factoring 1/6 from these terms, I get 1/6 times 2v plus u. Note that this looks very similar to the vector mr that we found above. In fact, we can write the vector tm as 1/2 times 1/3 times u plus 2v, which is 1/2 of the vector mr. So we see here that the vector tm is a scalar multiple of the vector mr. So this tells me that these vectors point in the same direction. We can also look at the vector tr. Well, tr is just the sum of the vector tm plus the vector mr. Well, from above we found that Tm is 1/2 mr, and then we have plus mr. So overall, the vector Tr is 3/2 mr. So we see here that the vector Tr is also a scalar multiple of the vector mr. So the three vectors Tm, mr, and Tr are all scalar multiples of each other, which proves that the points T, M, and R are collinear.